Unbalanced currents refer to a condition where the currents flowing in the individual conductors of a multi-phase electrical system are not of equal magnitude. In a balanced system, the currents in all phases are equal and displaced by 120 degrees. However, deviations from this ideal condition, such as uneven distribution of loads or phase imbalances, can result in imbalanced currents. Consider a three-phase electrical system. If the current in phase A, denoted as IA, is significantly higher than the currents in phase B, denoted as IB, and phase C, denoted as IC, this indicates an imbalance. This imbalance can be caused by factors such as, firstly, unequal loads in different phases, secondly, malfunctions in equipment or wiring, and thirdly, imbalances in transformer connections. Unbalanced currents can have several adverse effects on electrical equipment and the system as a whole. Firstly, overheating of conductors and transformers due to excessive current flow can occur. Secondly, the efficiency of electrical equipment can be reduced. Thirdly, voltage fluctuations and harmonics can be introduced into the system. Fourthly, increased neutral current can result, potentially overloading the neutral conductor. Fifthly, premature failure of equipment can occur. NEC 310.15 B4 requires that conductors in multi-phase systems be calculated for the maximum unbalanced current. This is the maximum of the maximum current in any one conductor and 1.4 times the maximum current in the other conductors. This requirement ensures that the conductors are adequately sized to handle the unbalanced currents that may occur in the system. Understanding the concept of unbalanced currents is crucial for ensuring the safe and efficient operation of electrical systems. Ignoring this aspect can lead to potential hazards and equipment damage. When dealing with multi-phase systems, always consider the possibility of unbalanced currents and take appropriate measures to mitigate their effects. This includes properly sizing conductors, balancing loads as much as possible, and regularly inspecting equipment for any signs of malfunction. In practical applications, consider a scenario where a three-phase motor is connected to an unbalanced load. For instance, if one phase of the motor is drawing significantly more current than the other two, this indicates an unbalanced condition. This can be due to various reasons, such as a winding fault in the motor or an imbalance in the supply voltage. To address this issue, firstly, check the motor windings for any signs of damage or insulation breakdown. Secondly, verify the supply voltage to ensure that it is balanced across all three phases. Thirdly, consider using a phase balancing transformer to mitigate the effects of the unbalanced load. Another common scenario involves unbalanced loads in a distribution panel. If one phase of the panel is heavily loaded while the other two are lightly loaded, this can result in unbalanced currents in the supply conductors. To remedy this, firstly, redistribute the loads to balance them across all three phases. Secondly, consider using a larger conductor size for the neutral conductor to accommodate the increased neutral current. Thirdly, implement a monitoring system to detect and alert you to any significant imbalances in the system. When calculating conductor sizes for unbalanced loads, it is essential to follow the guidelines outlined in NEC 310.15 B4. This requires determining the maximum current in any one conductor and then calculating 1.4 times the maximum current in the other conductors. The larger of these two values should be used as the basis for selecting the appropriate conductor size. In addition to conductor sizing, it is also important to consider the impact of unbalanced currents on transformers. Unbalanced currents can cause transformers to overheat and operate inefficiently. To mitigate this, firstly, ensure that the transformer is properly sized for the load. Secondly, consider using a transformer with a higher K factor to handle harmonic currents. Thirdly, implement a monitoring system to detect and alert you to any signs of transformer overloading or overheating. Furthermore, unbalanced currents can also affect the performance of sensitive electronic equipment. Voltage fluctuations and harmonics caused by unbalanced currents can disrupt the operation of these devices and potentially damage them. To address this, firstly, install a power conditioner or voltage regulator to stabilize the voltage supply. Secondly, use a harmonic filter to reduce the levels of harmonic currents in the system. Thirdly, ensure that the equipment is properly grounded to minimize the effects of electrical noise. In conclusion, unbalanced currents are a common issue in multi-phase electrical systems that can have significant consequences if not addressed properly. By understanding the causes, effects, and mitigation techniques for unbalanced currents, you can ensure the safe and efficient operation of your electrical systems. Remember to always consult with a qualified electrician or electrical engineer for any specific questions or concerns related to unbalanced currents in your system. Regular inspections and maintenance are also essential for detecting and addressing any potential issues before they escalate into major problems. For example, consider a commercial building with multiple tenants, each having different electrical loads. If one tenant has a large number of single-phase loads connected to one phase of the building's electrical system, it can create a significant imbalance. This can lead to voltage drops on that particular phase, affecting the performance of equipment connected to it. To mitigate this, the building owner or electrical contractor could redistribute the loads among the three phases, ensuring that each phase carries a similar amount of current. This would help to balance the system and improve overall performance. Another example is an industrial facility with heavy machinery that operates on three-phase power. If one of the machines has a faulty winding or an unbalanced load, it can cause unbalanced currents to flow back into the electrical system. This can affect the operation of other equipment in the facility and even cause damage to the power grid. To address this, the facility's electrical maintenance team should regularly inspect the machines for any signs of faults or imbalances. They should also use power quality monitoring equipment to detect and analyze any unbalanced currents in the system. If an imbalance is detected, they should take corrective action, such as repairing the machine or balancing the load. In agricultural settings, irrigation pumps often run on three-phase power. If the pumps are not properly maintained or if the power supply is unreliable, it can lead to unbalanced currents. This can cause the pumps to overheat and fail prematurely, disrupting irrigation schedules and affecting crop yields. To prevent this, farmers should ensure that their irrigation pumps are regularly inspected and maintained. They should also use surge protectors and voltage regulators to protect the pumps from power surges and voltage fluctuations. Furthermore, in residential buildings with solar panels, unbalanced currents can occur if the solar panels are not evenly distributed among the three phases of the electrical system. This can lead to voltage imbalances and affect the performance of appliances connected to the system. To address this, solar panel installers should carefully plan the installation to ensure that the solar panels are evenly distributed among the three phases. They should also use a three-phase inverter to convert the DC power from the solar panels into balanced AC power. In data centers, where uptime is critical, unbalanced currents can be a major concern. Unbalanced loads can cause voltage fluctuations and harmonics, which can disrupt the operation of sensitive electronic equipment. To mitigate this, data center operators should use power distribution units with built-in load balancing capabilities. They should also use uninterruptible power supplies to provide backup power in case of a power outage. Furthermore, they should regularly monitor the power quality of the system to detect and address any imbalances or harmonics. In healthcare facilities, where reliable power is essential for patient care, unbalanced currents can pose a serious risk. Voltage fluctuations and harmonics can disrupt the operation of medical equipment, potentially endangering patients' lives. To prevent this, healthcare facilities should use redundant power systems and uninterruptible power supplies to ensure a continuous supply of clean power. They should also regularly inspect and maintain their electrical systems to detect and address any potential issues. Remember that NEC 310.15 B4 is just one aspect of electrical safety and code compliance. It is important to consult with a qualified electrician or electrical engineer to ensure that your electrical system meets all applicable requirements. They can help you to identify and address any potential hazards and ensure the safe and reliable operation of your electrical system. In summary, dealing with unbalanced currents requires a multifaceted approach that includes firstly, proper load balancing, secondly, regular inspections and maintenance, thirdly, the use of appropriate equipment and technologies, and fourthly, compliance with relevant codes and standards. By taking these steps, you can minimize the risks associated with unbalanced currents and ensure the safe and efficient operation of your electrical systems.